Hey, welcome. Today, we're diving deep into one of the most important, most versatile, and honestly, one of the most fascinating elements in the entire universe. Carbon. You know, it's the foundation for pretty much everything, from our own bodies to the fuel that powers our cars. So let's get right into what makes this element so incredibly special. So, to get us started, I've got a little riddle for you. On the surface, what could a person, the soft graphite in a pencil, and the hardest substance known to science possibly have in common? I mean, they couldn't seem more different, right? But they all share one fundamental secret.
And there it is. The answer is the element carbon. That's right, all of them. The unbelievable variety we see in the world around us, soft stuff, hard stuff, living things, inanimate objects, so much of it is built from the exact same atomic starting point. And that just brings up a massive question. How is that even possible? Well, this is where it gets kind of weird. For an element that is so central to, well, everything, it's shockingly rare. We call this the carbon paradox. Just look at these numbers. The Earth's crust is only 0.02% carbon. The atmosphere, a tiny 0.03%. So how on earth does an element this scarce become the undisputed king of chemistry?
We're going to solve that paradox together, step by step. First, we'll uncover carbon's unique way of making friends with other atoms. It's all about sharing. Then, we'll get into its two chemical superpowers, see the incredible structures it can build, and finally, we'll pull it all together to see why it's the essential building block for life itself. Okay, so first things first. To really get a handle on carbon, you have to understand how atoms connect with each other. It really all boils down to their electrons and the bonds that they form.
Generally speaking, atoms have two main ways they hook up. The first is called an ionic bond. That's where one atom literally gives an electron to another. It's a total transaction. This creates charged particles we call ions and makes stuff with really high melting points, like your everyday table salt. But carbon does things differently. It prefers to share its electrons, forming what we call covalent bonds. This creates much weaker forces between the molecules, which is why they have lower melting points. And this choice to share, that's the first major clue to its power.
So why does carbon choose to share? Well, it's not really a choice. It's more of a necessity. See, atoms are happiest when they have a full outer shell of electrons. Carbon has 4 in its outer shell. So to get a full shell, it could try to gain 4 more, but that's a lot for its small nucleus to hold on to. Or it could try to lose all 4, but that would take a ridiculous amount of energy. Neither option is good. So the only efficient solution left is to share its 4 electrons with other atoms.
And that brings us to the official definition right from the source material. A covalent bond is just an electron pair that's shared between two atoms. It's a partnership, not a giveaway. And this simple act of sharing, well, it's the entire foundation for everything that makes carbon so versatile.
Okay, so because carbon can form these 4 super stable, sharing-based bonds, it unlocks 2 incredible properties, 2 genuine chemical superpowers that pretty much no other element has to the same degree.
The first superpower is called catenation. And honestly, the best way to think about it is carbon's amazing ability to hold hands with itself over and over and over again, forming these incredibly long and stable chains. The carbon-carbon bond is just so strong that it can create these massive molecules without them falling apart.
Its second superpower is tetravalency. Now, tetra just means 4. Simple enough, right? Because it has 4 outer electrons to share, it can form 4 separate bonds at the exact same time. This basically makes a carbon atom like a universal Lego brick with 4 connection points. It can build not just in a straight line, but in any direction, up, down, left, right, you name it.
So what happens when you combine these 2 superpowers, the ability to form long chains and the ability to branch out in 4 directions? Well, the results are absolutely stunning. You get a world of almost infinite variety, all built from this one single element.
This incredible ability for one single element to exist in these wildly different forms is a concept called allotropy. And carbon is the absolute master of this. By changing nothing more than how the carbon atoms are connected to each other, you can create materials with completely opposite properties.
And this right here is the ultimate example. It's just wild. In a diamond, every single carbon atom is bonded tightly to 4 other carbon atoms. This creates this super powerful, rigid 3D lattice, making it the hardest substance we know of. But in graphite, the stuff in your pencil, each carbon only bonds to 3 others. This forms these flat, hexagonal sheets that can just slide right over each other, which is what makes it so soft and slippery. Same atoms, completely different worlds. It's amazing.
So here, you can see catenation, that chain-making ability in its simplest form. We've got one carbon with some hydrogens, and that's methane. Link two carbons together, you get ethane. 3 gives you propane, and 4 gives you butane. This ability to just keep adding to the chain is totally fundamental to how it all works.
But of course, it doesn't stop with simple, straight lines. Thanks to its tetravalency, its 4 connection points, these chains can be branched. You can get these structures with the same number of atoms but totally different shapes, which we call isomers. And even crazier, the chains can loop back and connect to themselves, forming super stable rings like cyclohexane or benzene. The possibilities really are endless.
So we've seen how carbon bonds and the amazing structures it can form. But what's the big deal? Why does this actually matter to you and me? Let's connect all this chemistry back to the world we live in and to life itself.
The sheer scale of this is, well, it's hard to wrap your head around. Chemists have identified millions upon millions of distinct carbon compounds. That number absolutely dwarfs the compounds formed by all the other elements on the periodic table combined. Carbon isn't just another player in chemistry, it's in a league of its own.
So, it all comes back to these core properties. Its love for strong covalent bonds creates stable molecules. Catenation lets it build long and complex chains and rings. Tetravalency lets it branch out and create complex 3D shapes. And there's one more key detail. Carbon is a small atom. That means its nucleus has a really tight grip on those shared electrons, making its bonds exceptionally strong and stable.
And this isn't just some abstract concept from a chemistry book. These properties are exactly why carbon forms the backbone of everything. The complex molecules in the food you eat, the fibers in the clothes you're wearing, the active ingredients in medicines, they are all these intricate structures built on carbon chains and rings. Every living thing we know of is carbon-based. We are quite literally made of this stuff.
So, it all comes full circle. From just a few simple rules, sharing 4 electrons and linking together, carbon creates a nearly infinite complexity that is the foundation for all of life and technology as we know it. And that leaves us with a pretty fascinating thought, doesn't it? Knowing everything we know about carbon's potential, what incredible new materials are just waiting for us to design and build with this humble and absolutely amazing element.